questions that come up during the discussion, please don't hesitate to interrupt with those questions. Sometimes it's something I said that doesn't make sense, maybe because I said something wrong, but sometimes it's because it needs more explanation. If you're watching from home or by delayed viewing, and you have questions that come up after this class ends, please don't hesitate to email me. I also have office hours today from 1 to 4 p.m., so if you're available during that time, or not today, yesterday. Never mind, I have office hours next week. Boy, I'm tired today. I have office hours next week on Tuesdays and Wednesdays from 1 to 4 p.m., and you're welcome to pop into any of those. If you let me know in advance, I'll make sure that I'm there waiting for you, but if not, it might be a minute or two if I'm collecting copies or talking to a professor down the hall or whatever it might be. All right, so in that case, let's jump right back into the discussion from last week. In fact, let me back this up just a little bit just to quickly go through as a recap. All right, so we talked about confidence intervals. We did the first two sections of this. The first was a confidence interval for proportions. And the key thing to realize there, what we're looking at is what percentage fit one category out of two possibilities. So the most likely scenario there is something like a survey where we're trying to do a political support. Which candidate do you support, or do you support or oppose a certain bill? That would be a survey for proportion. Sorry, excuse me. And we talked about the differences. In fact, I'll just go through this in just a moment. We talked about the differences between being more sure that your interval contains the true value, the one you're trying to estimate about the population as a whole, versus being more precise and having a narrower window. There's a trade-off there. I can either be very sure that I have the correct value somewhere in my interval, or I can be very precise. It's very difficult to be both unless I have a very robust sample. All right. We also talked about confidence intervals for means in this situation where I know the population standard deviation and I have a large enough sample size. And we'll go through that just quickly in a moment. Today we're going to talk about what to do when we don't know the population standard deviation or when we don't have a large enough sample. All right. We talked briefly about how to interpret these things, and it's really important that the interval is just giving us a likely window in which we expect to find the population value, whether it's a population proportion or a population mean. We don't have a guarantee that it's in that window, we just have a likelihood, and that likelihood is our confidence level. So if we are 95% confident, if we're doing a 95% confidence interval, then we can be 95% confident that our interval contains the true value, but we still have the possibility that we just happen to get an unlucky sample, and in that 5% situation, our interval will not contain the true value. And so even when you see this margin of error presented, that's basically saying how much wiggle room on either side for that 95% confidence interval. It still could be outside of that window, and in fact we'd expect it to be about 5% of the time if it's a 95% confidence interval. Okay. Now for proportions, remember the equivalent of the standard deviation for the sample proportion is this standard error, which is calculated as the square root of p hat times q hat over n. P hat is the success rate or support rate if you'd like, and q hat is its complement. It's the failure rate or the opposition rate. So if I have 60% who say they do believe in evolution, then I'd have 0.6 for my p and 0.4 for my q. 60% do, 40% do not. And that allows us then to build a sampling distribution for proportions. This is what we'd expect to find from that population. If this was the true population value, we'd expect to find samples distributed like this, clustered around the center, which is the value we observed. But occasionally we find a rare sample that gives us a particularly high support rate or a particularly low support rate. We have to find a critical value, which tells us how far or how many standard deviations, how many standard errors to the left or to the right we need to go to collect the middle, whatever percent we're looking for. And it's different for different confidence intervals. For a 90% confidence interval, I use Z star as 1.645. For a 95% confidence interval, I use 1.96. And I showed you on Wagner's calculator how to find the the critical value for any confidence level that you need. Essentially what you do is you choose the middle value. You make sure to use the 0 and 1, the standard normal distribution. So 0 for the mean, 1 for the standard deviation. And then you type in the blue area in the middle whatever percentage you want. If you want 95%, it'd be 0.95. And then in the red box, it will tell you 1.96 and changed. I think it's 1.96002 or something like that. Sorry, I'm losing my voice today. All right. Once we have that, again, that tells us how many standard errors. So the margin of error, the amount we allow above and below to build our confidence interval, is that many of the standard errors. So take that critical value and multiply it by the standard error to get the total width on either side. We did an example. Talk through all of that. This is that trade-off I was talking about. If you want to be, let's raise this just a bit, lower it a bit. Version problems in video. It's interesting. So if we want to ensure that we're more likely to capture the true value, we can widen that interval. But in doing so, we have a less precise estimate. We have a wider interval. On the other hand, if we want a narrower interval so we can be more precise with our estimate, then we are going to have to accept the fact that we are less likely to contain the true value. So there's that trade-off between certainty that it's inside my confidence interval, the thing I'm trying to estimate is inside the confidence interval, versus precision, having a tight window to look at. All right. This is a discussion of the critical values. We already talked through that. I'm going to go through a lot over and over again. I do want to hit the assumptions and conditions necessary for each one because this is really important to check before you do anything with it. Whenever we're looking for a confidence interval, if we're using the normal model, so we're using a Z distribution, we need to check the independence assumption, which we almost never check directly. It's very hard to do so. So most of the time what we'll do there is we'll use the randomization condition. If our sample is constructed with enough randomization, then we'll assume that that's enough to give us independence. We also need to check the 10% condition. That is our sample, the number of elements in our sample, the number of people we surveyed, if that's what it is, or the number of objects we measured, if we're doing a mean. We need to check the 10% condition, but that does not comprise 10% or more of the overall population. If it does, then our sampling distribution is no longer necessarily normal. That is, the central limit theorem kind of breaks down a little bit when we have too large of a sample. Instead of getting a normal distribution, we get a distribution that looks a lot more like the sample, like the population itself, which may not be distributed normally. Okay. Lastly, in the case of proportions, we need to check the success or failure condition. And what that means is we want to expect at least 10 successes or 10 failures in our sample. So if you're doing this beforehand and you don't know what you're going to see, you want to use an estimate for the number of the percentage of successes and percentage of failures, and multiply that by your sample size. Guarantee that in both cases, both for P times N and Q times N, you get at least 10. If you actually collect a sample, make sure your sample includes at least 10 who support it and 10 who do not, or 10 successes and 10 failures. As long as that's the case, you've passed the success and failure condition. Once that happens, we get the central limit theorem applying to our sampling distribution, so we can build a model for what we'd expect to see from samples if we did this over and over again. And we can then use that to construct our confidence interval. So the margin of error is exactly what I said before. It's the critical value as a number of standard errors times the standard error. And we take our midpoint, the one we observe in the sample, as the point estimate. So we take that plus the margin of error to get the upper limit, and that minus the margin of error to get the lower limit. We did a couple of examples. And when we do the confidence interval for means, we end up doing the same kind of thing. We have to check the independence assumption. We have to check the 10% condition. And that's basically it, as long as we have a large enough sample. If our sample's too small, then unfortunately there's some variation that we can't really account for, and that's partially because the central limit theorem applies as the sample size grows. It gets closer and closer to a true normal distribution. So if it's too small, we don't have enough room to see that. But in practice, if our sample size is 30 or more, that's good enough. And in that case, we do get the normal distribution we expect. Similar to what happens with proportions, the sampling distribution will be normally distributed around the true value. So the center will be the true value again. But now my standard error for the mean is the population standard deviation scaled down by the square root of the sample size. So take sigma and divide by the square root of n when you know sigma. So that's the standard error of the mean. It takes the role of the standard error in the proportions question just a moment ago, and everything else works exactly the same. Once I've checked the right conditions, I know I have the normal distribution. I need to have the equivalent of my standard deviation, which in this case is the standard error for the mean, sigma over the square root of n. Then I find my critical value corresponding to the, my point estimate is what comes from my sample. That's the mean I observed in the sample itself. So I'll usually use the X bar notation for that. And I build my margin of error by taking the critical z-score, which is how many standard deviations I need for the desired confidence level. I want the middle 95% for a 95% confidence interval. So I would use 1.96. It's the same z-score as we saw before. If I want the middle 90%, I use 1.645, the same ones we saw before as well. And again, you can calculate each of those using Wagner's calculator if you do the normal standard distribution. So 0 for the mean, 1 for the standard deviation, and then check for the area in the blue box to find the critical value in the red box. And I'll show you that again in just a moment. All right, then you construct the margin of error just by multiplying those two things. Take the critical value times the standard error, critical z-score, times the standard error. And if you add that to the point estimate, you get the amount above. And if you subtract that from the point estimate, you get the boundary below. And between those two numbers is your confidence interval. So very, very similar to what we did with proportions. We're just estimating a mean instead. And in this situation, we can use the same distribution, the normal distribution we've been using thus far. We did a few examples of that. So here's the same collection of critical values. Here's the 3 ways to write it. It is important to be able to translate those. And this will be true also for the last type of confidence interval we'll talk about in just a bit. What we're saying is that we have 95% confidence, for instance, that our mean, our population mean, is in the interval x bar plus or minus the margin of error. So that's one way to write it. Take your point estimate and add or subtract the margin of error. Another way to write it is actually to do that. Subtract the margin of error to get the lower limit, add the margin of error to get the upper limit, and just list those two things inside parentheses. And then the last way to do it is to write it as a tri-inequality. So you take that lower limit, less than or equal to the thing I'm trying to estimate, less than or equal to the upper limit. And by the way, usually we won't use this capital X bar notation. We'll usually use mu, because it's the population mean we're trying to estimate. But I chose to write capital X bar to try to emphasize to you that it's really, this is what we're estimating from the sample, and this is what we're trying to understand from the population. Okay. Usually we'll use a mu here, and that's what you'll see in the book. And we did an example there, and another example there. Okay. Interpretations. I am 95% confident that the thing I'm trying to estimate is between the lower limit and the upper limit. That's the general form you will always use, whether it's for proportions or for means. And in fact, even in the last case that we'll talk about later, you'll use exactly the same description for your interpretations. All right. We did that last question there as well. Any questions on what we've covered so far? This is all just a highlight from what we've done before. So this one slide here at the start of the third section is really just kind of summarizing what we've already seen. So we have to check the assumptions that we need before we know we have the distribution that allows us to build these confidence intervals. The first thing to check is the independence assumption. The second thing to check is the 10% condition. And if you're looking at a proportions question, you also need to check the success or failure condition. Okay? And then as long as your sample size is large enough, you can use a normal model for the sampling distribution. Okay? If you're doing proportions, then the normal model is a normal distribution centered around the true value with an equivalent of standard deviation being the square root of PQ over n. Again, the success rate times the failure rate over the sample size. If you don't have those things from the population, then you can use them from the sample and everything works out just fine. And that's how we build the confidence intervals. In the case of means, it'll be normally distributed around the true center, the true mean. So if this is the population mean, then our sample distribution will be centered around that value. And the equivalent of the standard deviation will be sigma over the square root of n, where sigma is the population standard deviation and n is the sample size. So larger samples will have less variation. They'll be more tightly clustered around the true value. Okay. All right, any questions about that? All right, so if you think about how this works, it's not too hard to understand why the proportions distribution is very valuable. Right? If I'm a surveyor and I want to understand, maybe politically, what the support for a particular bill might be, how many people are likely to vote for it or against it, I can simply do a phone survey, and if I'm careful about how I construct the sample itself so that there's enough randomization, and that it doesn't comprise 10% or more of the population, and that I find at least 10 who support it and 10 who don't support it, then I can build a confidence interval pretty quickly. Actually, it doesn't take much work at all. That gives me a good estimate for the likely support level among the general population for that bill. So then I can predict, is it likely to pass or not? If I find that the support level is 58% plus or minus 4% with a 95% confidence interval, I'm pretty sure that it's going to pass because the chances of it falling below 50% are pretty low. That's more than 2 standard deviations below. In fact, it's at that point, if it's 3% is essentially 2 standard deviations. I would be almost 5 standard deviations below. That can happen, but it's pretty rare, and you can find the probability of that. In fact, we'll talk about that a little bit later today, because that will be what underpins the ideas in hypothesis testing next week. All right. So, did I want to do this now? Okay. Yeah, actually this will help with highlighting the population, the sampling distribution. So let's do that. So suppose I work as a manager for a grocery store, and I want to understand the likelihood that I will have 10 customers this afternoon who spend an average of $40. And what I do is I look at my records, and I can see that on Sundays, which happens to be the day I'm looking at here, my customer purchases are averaging $32 and have a standard deviation of $20. Right, so I have a lot of people who come in and buy a few things and then leave. Nobody's doing their major shop, I guess, on these Sundays. What's the probability that the next 10 will spend an average of $40? So how can I check that? Well, what I will want to do is I want to think about whether that next 10 as a sample, having a sample average of 40 would be an unusual event. Okay? Now there's a few things I have to do here. First, I need to check those conditions. So let's think about first the independence assumption. Are those next 10 customers going to be independent of each other? What do you think?
Yes. They might spend.
Yeah, but maybe, like, so for instance, sometimes I take my kids with me and they want to buy something separate. So they might go through in the line separately from me. Are they going to be independent from me? Not necessarily, right? But in practice, it's probably a safe enough assumption. Is it a randomized sample? also not necessarily clear. If that Sunday happens to be, I don't know, the day before Valentine's Day, you'll have a lot of guys coming in and buying these bouquets of flowers. If it's Super Bowl Sunday, you might have a lot of people coming in and buying, I don't know, a six-pack of beer or some chips or something like that day. Hopefully they bought some stuff the day before instead, but you never know. There's lots of reasons why I could see that a particular day it might not be necessarily a randomized sample. But with no other information here, it seems like it might be a safe assumption that most of the time it would be essentially random or random enough. Okay, so let's just take that for granted. What about the other conditions to check here? I'm looking at a mean, so I need, first of all, a boy, I am having a rough day here. I need no more than 10% of the population. So what is this? 10 customers. I want 10 customers to be no more than 10% of the population I'm trying to estimate, which I guess is Sunday customers at this grocery store. Well, hopefully we have more than 100 customers. If we don't, we're probably not doing a lot of business. We probably won't be in business for very long. So I'm going to assume that that's probably no more than 10%. And then the last thing to check in this situation is I need to have at least 30 in my sample. And do I have that here? No, I have 10. So this is a little bit dubious, okay? I'm going to show you how to do this for now, but be aware we're actually going to have to use a different distribution, and that other distribution will change this ever so slightly, okay? But for the sake of illustrating how the sampling distributions work, I'm going to assume that 10 is enough in this one situation, just so you can see how this plays out, because again, it will help us understand what we're doing next. All right, so I want to find the probability that the next 10 will spend an average of $40. So let's write down what we know here. We're looking at a population mean of $32, a population standard deviation of 20, and a sample size of 10. And what we're asking about is the probability that our sample distribution is 40. So what I'll say is greater than or equal to 40, right? Remember, for a continuous variable, the probability that it's equal to a specific value is 0. Right? Now this is technically not quite continuous because I can't have $40 and 11.23 cents. They're not going to charge me that. They'll just charge me the 12 cents. But we're going to treat it as a continuous variable just for the sake of the discussion here today. All right, so how do I find this probability? Well, first I need to find the distribution of these sample means. So under the assumption that those conditions are satisfied, my sample means should be normally distributed around the true value with a standard deviation or a standard error of the mean equivalent to sigma over the square root of n. Okay. So what are those values for this particular example? Well, the mean in the population is 32, so that should be the center of my sample means. They should all be clustered close to 32. How close? Well, sigma over the square root of n gives me a feel for the standard error, the equivalent of the standard deviation in this case. So that would be 20 over the square root of 10. Now from that, I can compute the likelihood of 40 or more, and what I can do is I can compute a z-score, and then find what the probability of that z-score would be. So let's see how I do that. Remember, when you compute a z-score, it's always the observed minus the expected over the standard deviation, or the equivalent of it. So what are those players in this particular situation? The observed amount that I'm looking for is the 40. What I would expect most of the time is the center of my distribution here, 32. And the equivalent of my standard deviation is this standard error, 20 over the square root of 10. I'll write it sideways so it's clear that that's all under the denominator here. Okay. Well, so what is that as a z-score? Let me quickly calculate this. 40 minus 32 is 8. 20 over the square root of 10 is about 6.3245. And so if I take 8 divided by that, I get approximately 1.26491. Okay. There's more digits than that, but for now I'm just going to leave it at that. How can I find the probability that z is at least that large? 2.6491, sorry. Remember what I'm doing here. I'm looking at my normal distribution. I calculated this z-score of 1.26, let's say 265. And I'm trying to find this area right here. That will be the probability that I'm looking for. So I can use my preferred calculator to find the area on the right side, and the right tail, for this particular z-score. I will jump over to Wagner's calculator. Let's jump to the computer if that's alright, so you can see how that calculation works. So I'm doing a normal distribution. For now, I'm just going to show you what the z-score, and then I'll show you how to do it without having to go through the z-score along the way.
Here's who's eligible.
So I want to find the probability that it's greater than the boundary value I'm looking at, so that'll be the right-hand tail. And the value I just calculated is 1.26491. And so when I do that, I get an area of 0.10295. And so that is the probability that I'll see a sample that is that high or higher in the next 10 customers. What would happen if I had more customers, if I was looking for an average of 40 among 20 customers? Well, in that case, my standard error would be 20 over the square root of 20. And so that would be a tighter window, and that would make this less likely. The tail would have even less area that far out, because the distribution itself would tighten around the center. So that sampling distribution idea, that's what we're using when we build confidence intervals. That is also what we'll be using when we ask, how unusual is the sample I just saw? Okay. That is the key idea in hypothesis testing for next week. All right, so let's check and see, does that line up with what I had in the slides? Okay. Well, I mentioned a couple problems on that previous example. One of them is the sample size is very small. That is kind of important. But another problem in practice is if I'm trying to estimate something about a population, and I need to use maybe I'm trying to estimate the mean for the population, and I need to use the standard deviation from the population to do it, how do I get the standard deviation? Do you want to remember the formula for that? If you don't, let me write it down really quickly. So if I want the variance, let's say mu is my population mean, right? And then I'll use x to represent each individual value. What I want to do is I want to add up, that's my sigma here, x minus the mean squared, and then take 1 over the number in my population. So n is the number in the population. So over all the x's in the population. There's a problem with that. In order to calculate, so this is sigma squared, I want sigma, the square root of that, I want to calculate this population standard deviation, I have to know the population mean to do it. And more than that, I have to know every single population value to calculate this whole thing. So why am I trying to estimate the mean if I already know it? Right? So in practice, this is not usually the way we do it. There are situations where maybe, like I think I gave you an example last week with ACT scores, for instance. If I want to do a confidence interval for ACT scores, I can use previous year's data, where I might have all the data. Right? And then from that, I can assume that my standard deviation is essentially the same as it was from last year, and then ask about whether the mean would be likely to be in a certain region or not. It's possible to do that. In the case of the grocery store manager, I might have many, many Sundays worth of data. And so even though that won't actually be my sigma, including this next 10 customers, or all the customers from today, for instance, if it includes all the customers from the last 5 years, I'm probably pretty confident that the sigma value is not going to change that much. So I could use it in that situation, but at that point, I actually have the mean for those last 5 years, and the mean isn't going to change that much either. So if I'm trying to estimate the mean, this doesn't help me very much. So how do we get around that? If we don't have the population standard deviation, is there something else we can use to estimate the population standard deviation? What do you think? So I collect a sample, let's say, of 10 customers. If I didn't have the population standard deviation, is there something I could do, maybe even with that sample, that would help me estimate the population standard deviation?
Why are you coming to me?
Oh man, I wanted to see what was the
Okay. Well, let's jump back to the document cam for a moment. If we look at this formula, the things we don't know, we don't have access to every single population value, x. And we don't have access to the population mean. But what we could use is our sample. Right? We do have access to all the members of our sample because that's what a sample is. We've collected the data about those individuals. And so I could add up across all the members of the sample, the member minus the sample mean, as kind of a stand-in for mu. Right? And in fact, if we do that and we use n minus 1 instead of n, you may remember that's how we got the sample standard deviation. All right? I think I tried to talk about this, but there's a number of ways to realize why, but the key idea here that we use an n minus 1 rather than an n is because I have a small number, maybe 10, in my sample here. Those 10 were used in calculating the sample mean, and so they are likely to be closer to the sample mean than they are necessarily to the population mean, because I'm guaranteed that they're all going to be clustered around this. They were used to calculate this. If you go through a number of calculations involving the expected value and the variance, you can actually show that if you want what's called an unbiased estimator, that is, it's not likely to be biased in one direction or the other, for the population standard deviation, you want to use n minus 1 instead of n here. And if you do that, that's why it works. That's why we actually use the n minus 1 here for s. Don't worry about the details there. I just wanted to mention that. So it would be nice if I could just use this. And in that case, what I'd be trying to do is I'd be trying to say, well, maybe my sample mean distribution is normally distributed around the mean with s over the square root of n. All right? This is a question. That's what I'd like to do. And for a while, people actually tried to do this. Statisticians who were collecting information tried to do things like this. And they found that it didn't really work the way it seemed like it should. One possible problem is if your sample size is small, But even when your sample size is large, it turns out that this S, it's not a perfect stand-in because it's not going to be necessarily the same as sigma, right? It's an estimate for sigma, but there's more variation in that estimate. And that extra variation, unfortunately, breaks this normal distribution we'd like to see. This really does not work. If you want to use S in place of the normal, in place of sigma, you don't get a normal distribution anymore. So let's jump back to the slides and we'll talk about how that discovery came about and what it means for us. So the key idea is we'd like to use sigma because that's what's important in terms of the standard error for the mean. So we'd like to use sigma in building those confidence intervals and also later in computing hypothesis tests. But it's really hard to find sigma unless you have all of the population data already. And if you have all the population data already and you're doing calculations with every single data point, why would you be trying to estimate the mean? You can calculate it directly if you have all that data. So in practice, this is really pretty hard to find, and it's highly unlikely you actually have access to the exact value of sigma. Maybe you have a good estimate. In that case, you can use it, but you have to realize the reliability of what you build from that is subject to the reliability of your estimate. So what can we do instead? Well, we'd like to use S as a stand-in for sigma, because it's supposed to estimate the population standard deviation, and it comes from the sample whose data I already have. Right? If I'm collecting information about that sample for the purposes of calculation, I already have S. It's very easy to calculate, very easy to use. I can then build a sampling distribution based on S over the square root of n as my standard error for the mean. But if I do, I don't quite get a normal distribution, and that's the problem. And it's especially noticeable when the sample size is small. Okay. So, how do we handle that? Well, so here's a little bit of history about it. The first person who actually really explored this issue, his name was William Gossett, and he worked, interestingly, for Guinness, the brewery. And he was doing work testing the quality of the different batches that they were brewing. And he often had small sample sizes, and he was looking at the results he got, and they were not following the reliability that he expected to see from his studies in statistics. And so when he actually plotted what was happening, he saw that instead of actually seeing a normal distribution, he actually was seeing something that looked a lot like a normal distribution, but was a little shorter in the center and had thicker tails on both sides. And again, it was very noticeable when the when the sample size was small. But as the sample size grew, it got closer and closer to the true normal distribution that you're used to seeing. And so this is an example of the kind of distinction he was seeing in his studies. The dashed line here is the normal distribution. If you look at its probability density function, so that's the normal curve we're used to seeing. This solid line is the example he was observing when he had 3 as his sample size. Okay. So he ended up looking at this and studying it and publishing papers about it, but he published under a pseudonym. Student was the name that he used. And so for that reason, the distribution that he came up with, which he called a t-distribution, has the name the student's t-distribution. It's because he used the pseudonym student when he published this information. This is a student's t-distribution with 2 degrees of freedom. I'll explain how to calculate that in just a moment. But for now, just realize that that means the sample size is 3. So it's a very small sample. And unfortunately, what that does is it increases the variability away from the center. So what he did was he looked at the data he had, and he plotted it compared to the z-scores he would expect to see. And he realized it wasn't quite following a z-distribution, a normal distribution. Instead, he was getting something that looked, at least at first glance, like a normal distribution, but again, was a little flatter in the center and a little thicker in the tails. And again, it was more noticeable with smaller sample sizes. So he looked at the distributions that he had. This was the distribution of, so this is a particular example with heights. So these are the actual data values. and these are the means across samples. And if you plot those as test statistics, you'll find, yes, it looks somewhat like a normal distribution. It's unimodal and symmetric. But you'll also see that there's a lot more here with these large values and large negative values than we expect to see with a usual normal distribution. Right? We find 95% of the value between -2 and +2, negative 1.96 and positive 1.96 specifically, if it's a normal distribution. So I expect to find 95% right here and right here. But this looks like a little bit more than 5%. Okay? I think in this case he was using samples of size 10. So you can see that it's not quite the same. Again, thicker tails, slightly flatter center than a usual normal distribution would have. So, this is just explaining the idea. We're going to use S instead. This is the formula for S. Remember, it's the add up the deviations from the mean squared, divide that by n minus 1, and then take the square root to find the sample standard deviation. Excel will calculate this for you. In fact, Sparnar's calculator will calculate this for you if you have data, and I'll show you how to do that in just a few minutes. But that's what we're going to use as our stand-in for the population standard deviation. And when we do that, we can't use a normal distribution anymore. Instead, we have to use a t-distribution. Okay? So let me describe the t-distribution. First, there are two conditions you have to check to use a t-distribution. You first need to check the independence assumption. That's always there. So we want individual values inside the sample to be mutually independent. That is, we don't want the value of one member of our sample to be influential in any way on the value of another member of our sample. Incredibly hard to establish directly. We usually do it by randomizing our sample. If we have a sufficient amount of randomization there, we're going to assume that that implies independence. In the case of a t-distribution, all we need is a nearly normal condition. Because we're possibly working with small sample sizes, and we're also using a sample standard deviation to estimate the population values, we need a roughly normal distribution. So if you look at a distribution of the population values, you need that to look roughly normal. And roughly in this case essentially means, is it unimodal and symmetric? And if so, I'll call that good enough in this class. So that's the nearly normal condition. As long as you have those two conditions, then you can use a t-distribution to estimate the likelihood of a particular sample. Now, interestingly, as the sample size in your t-distribution gets larger and larger, in fact, after it hits 30 or more, it starts to look a lot like a normal distribution. And if you go beyond, I think, 100 in your sample, it's almost impossible to distinguish it from a normal distribution, at least to a few decimal places. So it turns out that this t-distribution is a good approximation to the normal distribution, but for small sample sizes. Okay. All right. So suppose we're in a situation where we know I don't have the population standard deviation, but I have those two conditions I needed to check satisfied. So I've collected a sample, and I want to build a confidence interval around it. Well, what I need to know is, how are the sampling distributions for means under this t-distribution distributed? Well, they're distributed pretty much exactly the way I would hope they would be. I can compute a test statistic by taking my observed value minus my expected value over the standard error. And in this case, the standard error is the closest equivalent I have to what I used in the previous confidence interval for means. In the previous one, I used sigma over the square root of n. Here I don't have sigma, so instead I'm going to use S over the square root of n. And if I do that, these test statistics will follow a t-distribution with n minus 1 degrees of freedom. Remember, n is my sample size, and so I need to know the number of degrees of freedom to look at the t-distribution that I need. Key idea here. Every different sample size has its own t-distribution, right? Every different number of degrees of freedom leads to a slightly different t-distribution. showed you a moment ago, this the solid line here is T with 2 degrees of freedom. At 3 degrees of freedom, it would be just a little bit taller and just a little bit thinner in the tails. 4 degrees of freedom would be even more so in both cases. And as the number of degrees of freedom goes to infinity, it approaches this dashed line, which is the z distribution, the normal distribution. All right. So once you've done this, once you've built these confidence intervals, you will then need to be able to interpret them. And remember, we're going to interpret them pretty much exactly the same way we interpreted them before. Okay? So just to make sure this is clear, some bad examples of interpretations that I've seen students do before. If you do a study, you might say, I find these two bounds in my confidence interval. 90% of all students sleep between 6.272 and 7.008 hours per night. That's not correct. And the reason is because that 90% is not a percentage of the students who fall in this area. It is a percentage of samples that I would find between these two values if the value halfway between them was the true population value. So it's not a percentage of students. I can't say that the mean amount of students sleep is 6.64 hours 90% of the time, because it either is that or it isn't that. Right? In fact, the chances of it being exactly that is exceptionally low. Chances are this is off by just a little bit, because this is what I calculated in my sample, and my sample doesn't have to be exactly the same as my population as a whole, especially if I have a small sample size. I can't even say that 90% of all samples will have a mean sleep between 6.272 and 7.008 hours per night, because that's only true if the 6.64 is the true center in the population. Right? When I build that sampling distribution, I have to have a center to start with, and then I can decide the middle 90% of all samples will be in a certain window. Right? And so only when I know that the center is truly here can I make this claim. On the other hand, what I can say is that I am 90% confident that the interval I computed contains the true value. Okay? And so you could say that 90% of all intervals that can be found in this way, that is, using this kind of data, would cover the true value, would contain the true value inside it. Or the way I suggested phrasing it, I am 90% confident that the true mean amount that students sleep is between 6.272 and 7.008 hours per night. So those are the best ways to interpret it. Okay. So, I do want to do some examples, but I'm noticing, now that the slides have finished, we're right at 9:50. So I think we should take a 5-minute break, and then we'll jump straight into, I built some GroupWorks designed around this, and so we'll do some practice problems there. Are there any questions before we take that break? All right, so it's now 9:51 on my clock. Let's return at 9:56. I'll see you in 5 minutes. Well, for proportions.
What?
Can we bring these toys out? Just show them to me? Ah! We pinky promise we won't lose them.
Yeah, I was gonna say those are small, so you leave them outside because they will ruin Grampy's tractor.
Yeah, we won't.
Okay.
Let's go get his shoes on. Yeah. I'm gonna put my toys over here. Put my toys over here if you want to set them down. Because I have to sit down in order to put my shoes on. And I put on. Why does your shoes go down? What? Oh, this is for. Bella, we have to shut the door so she doesn't get out. Let me get mine.
Bella!
Let me check again.
What are you doing?
Nope, it is not out. Hopefully Anderson doesn't see us. Wait, shut the door.